for the exam. It's good review for the final, and it's a good feedback for you in case you have questions. I do not change grades. I do not curve your exam. I do not make adjustments after I give you the grade. Therefore, it's very important for me to explain why you got what you got. Not everybody did well on this exam. Most people did pretty good, and I'm quite happy with what I see as a average for the class. However, there are many open questions for many people, things that they did not quite understand, and I would like to discuss those. First of all, the midterm exam was 11 questions, of which 10 were mandatory, so the maximum possible percentage-wise was 110%. Okay, so for somebody who did perfectly fine, they would have 110%. There is one person only who got the high. I cannot disclose his name, but I would like to say congratulations. I'm going to go ahead and solve the first each problem with you, for you. So you have had the function f of xy to be x squared minus y squared, and the differential was f sub x dx plus f sub y dy, which is 2x dx minus 2y dy. That was something very easy. It was not supposed to give you any headache, and most of you, the big majority of you, did a fine job on this one. What created some problems to most students was the second problem though. And I was sorry to hear that, and I'm sorry to see that. Find the directional derivative of a function, the same function as before. Same function, okay? So I have taken advantage of the previous problems in order to make your due time shorter. At the point P of coordinates x equals 0, y equals 1, you have a direction given by the vector. What does it mean, direction provided, given? I analyze that direction given by the vector means what? Not the vector I minus j. Why is that? Because this is not a unit vector. What is the corresponding direction given by it? The corresponding direction given by it is 1 over square root of 2i minus 1 over square root of j. So it's a collinear vector that is unitary. Say it again, Magdalena. The direction u represents a collinear vector, so pointing in the same direction as v, but it has to be unitary. Why? Because the definition of the directional derivative of a function along the direction u at the point P was given by the formula partial derivative at P times u1 plus partial derivative at P times u2. Did I expect you to write all this down? Yes, I did, as I showed you last time. So you have 2x evaluated at, what is x? 0, y1 times u1. This is u1 minus 2y evaluated at 0, 1 times minus 1 over root 2, which is u2. Well, that means the first term goes away because this is going to be 0. And output of second term, you have a plus y is 1, thank God, that's easy, 2 over square root of 2, the answer is root 2. So any other answer would normally receive a 0. The answer was B, square root 2. Now, on number 3, the problem, the function given is different, f of xy equals e to the xy. And they say the gradient of this function is at an arbitrary point. Say it again, the gradient of this function is at an arbitrary point. That was only part of a problem, a little bit of credit for just writing the gradient. This is actually easy, it's a piece of cake. Why is that? You have f sub xy plus f sub yj equals, Mendelina equals y e to the xy I plus x e to the xyj. That's very good. And that's very good. All right, okay, then this direction it's just the gradient, right? The direction corresponding to the gradient. They don't ask you for the u. Actually, you don't need the u. You just need the tangent plane in this case. And if you know the equation of the tangent plane, as I told you to remember that, that would be very helpful. Write your answers in the space provided. So what did I expect you to do? First this, and then write the equation z minus z0 equals f sub x times x minus x0 plus f sub y minus y0, where at the point P, evaluated at the point P. But attention, what is the point P? Where P is the origin, because we say at the origin. Oh, so that makes things easier. I'm not done. Half of the problem is still coming, so if you did until this point, I can only give you 5 out of 10 or something like that. Many people made a mistake at z0. Attention guys, when you plug in at 0, you don't get 0, for God's sake, you get 1, right? So z0 is 1. Now you're lucky in the sense that you have z minus 1 equals f sub x computed at 0, 0 will be 0, lucky you. F sub y computed at 0, 0. You were supposed to, you were expected to say that. So the answer for this problem was z equals 1. Still, if you messed up, I gave some partial credit because I didn't want to punish you too much, too harshly. On number 4, find the direction u. Now you're using number 3, so I should not erase number 3 completely, right? On number 4, you use number 3, so the same type of function, but it says find the direction in which this function increases most rapidly at the point 1, 1. Okay, so what do? You compute the gradient at the point 1, 1, and you say, all right, this is a piece of cake. It's going to be EI plus EJ EE. Wonderful. Good. So what you do is say u is gradient of f over the length of gradient of f at P, which is EE divided by the length of it. But you say, I don't have to compute the length of it. I know what is collinear to E is 1, 1. And no matter what you have here, you get the same unique result. Remember we talked about that uniqueness? This is what I try to emphasize, that you can have 7, 7, E, 9, 9, 5, 5, 100, and 100. If you divide by the norm, you still got the same answer. Not 1, 1, but 1 over root 2, 1 over root 2. So no matter what you had there, they could have had a million something instead of E, you still have the same U. Yes, put it back. Give yourself 5 points, modify that. But you, okay, so let me tell you. Normally I should penalize it because I say write the answer in the space provided. And thank God you had enough space, right? Look, this person wrote, I shouldn't show you who he is, he's not here anyway. He has space and he put I plus j over square root of 2. Because only 2 rows are enough to write that. It's okay. I understand you forgot to copy. My son did the same thing. He got a Scantron at the UIL competition. I thought I wanted to kill him, but it's okay. So he got all the answers right. And then the teacher, that reminds me of a movie with Mr. Bean, you know. So the teacher comes to him and says, well, your Scantron is blank. So what was I supposed to transfer all the answers you got in box, put them in the Scantron? Oh, really? So he goes quickly, and then he got only 75% of them transferred. The rest of them were not transferred. I don't know what they did. I have no idea. But TTU professor would have given full credit even for the answers that he wrote in box. But of what I understood, the rule for standardized exams like UIL is that if you don't have them on the Scantron, they don't count. This is very harsh because we don't do that. For example, in the final, if you, that's why I'm trying to read everything, okay, in the final. Suppose you box your answer, it's 1 over square root 2, whatever. And that's the right answer. And then you have A, B, C, D, multiple choice. And you forgot to circle 1 over square root of 2. I still give you 100% credit on that problem. But then some professors do not. So this is at the latitude of whoever makes the rules or whoever writes the exam. Okay. So again, for the final, even for the multiple choice problems, I still read the solutions. I'm going to ask you to use a blue book. Some professors do not ask you to use a blue book. They say, as long as you come right on the sheet, circle your answer, I'm fine. I'm not fine. I want to read what's in the blue book. So buy, how much is like $1? 5 blue books ahead of time, make sure you have it. Okie doke. Now, number 5 was a piece of cake once you did number 4. You have a question.
It matter what size for the final.
What
size blue book?
The big one. The bigger than that, right?
Okay.
The direction U for the, oh my God, 5. For the problem 4 was I plus j over root 2, right? This is what you remember that you did in problem 4. If you didn't do problem 4, you cannot do problem 5. Problem 5 says this is parallel to what line? This is parallel to, what is I plus j? Of course you think you don't have to draw that. I'm not expecting you to draw that. Y equals x is the first bisector. Okay, so the answer, all you had to do was circle C, and that was, once you circle C, you get full credit. If you don't do that, you don't get practically anything. Now, 6. What is the maximum rate of increase of the function z, the same of your friend, your fellow z equals e to the xy at p0, the coordinates 1, 1. The numerical value of the maximal rate of change is, and now, what's the simplest way to do it? There are 2 ways to do it. One is the long way, one's the short way. What's the short way, guys? Just compute the norm of the gradient the length of the gradient at the point P. So you have whatever that was, EE in length. So the answer was E root 2. Am I right?
Yep.
What was the long way? I saw somebody do it. This is a lot more work, but of course, would be to compute the directional derivative at the point P for this function, oh my God, in the direction of U, where U is the gradient divided by its length at the point P. And you get, of course, the same answer. Why? Because we proved that actually the maximum rate of change represents the directional derivative exactly in the direction given by the gradient. This is something we proved. One of the few things we proved in this class. All right, so the answer was E root 2. Let's move on to number 7. Number 7, and remind me of your 5 points, right? By email, can you email me so I have like an Excel sheet and I'll put it in. Consider the function f of xy e to the negative x squared negative y squared. What can you tell me about this type of function? It's the headache function, that if I would ask you to do an antiderivative of e to the negative x squared, you would say, Magdalena, didn't you say that this is impossible? That while the antiderivative exists, it cannot be expressed. Cannot be expressed as an elementary function. And that's a big headache. However, this problem is beautiful. Why is it beautiful? Because in the end it becomes magic. So it's a positive function. It's like a bell on top of the church something. And then you have to compute the double integral over the unit disk of center 0 and radius 1 of e to the negative x squared minus y squared dx dy. But then you say, well, I've done this kind of thing before, but not with Cartesian coordinates. We did it with the Jacobian R that changes everything into polar coordinates. So this guy becomes e to the minus r squared. E to the minus r squared r d theta being on a unit fat disk means the radius goes from 0 to 1. And this is a blessing for us because it's easy data. Then we have 0 to 2 pi. You could have put it in any order. For you, it's easier to close your eyes. When it comes to theta, say theta is independent. He's like a politician that has to do nothing with what's inside here. So let's pull him out of this picture, and he wants to live by himself. And the integral from 0 to 2 pi of 1 d theta, of course, was 2 pi. He's happy to go out, having fun. Look at his face. Now, this guy inside has to be thoroughly computed, in the sense that you perform the U substitution. I was actually amused that half of you, but exactly half of you, did U equals r squared, and half of you did U equals minus r squared. It really doesn't matter which one, but the problem is that some of you made a mess when you put the limit points back in place and you made mistakes. Somebody even got negative answers. I was about to fall off the chair, but of course, I was in a good mood because it was a holiday. I graded them. Fortunately, I graded them over the break. So after I came back from Georgia. So I have minus RDR. RDR was minus a half du. This fellow is just e to the u, and he's a blessing because the antiderivative is e to the u. So e to the u, however, taken between what and what? Not 0 and 1, but when you have 0 here, you have 0 here. When you have 1, you have minus 1. So attention that you have to pay a little bit of attention, otherwise you get something that makes no sense. times minus a half. That you will have to be careful about. Why? Because there will be a minus from here and a minus from here. In the end, the answer will be positive, and that reminded me of that silly plumber joke when you don't pay attention to the limits of integration, and you can get a minus volume or a minus area. So, e to the minus 1 minus 1. But that was negative number, but when you multiply by minus, you have 1 minus 1 over e. 1 minus 1 over e. Good. Thank God. This is a nice guy, less than 1. And this is key to your answer because 2 goes away and pi stays in place, and this is less than pi. So the answer to this question was an answer less than pi. And what if you didn't get it? I'm very sorry. You didn't get less than pi. You go no points. You get no points. But there were enough chances for you to get other points. I was broken-hearted for 10 people or more out of 25. Did not remember what I taught in class about that area of equilateral triangle, and it broke my heart, and I was about to cry, but I said, come on, they can do it better in the final. Honestly, I was broken-hearted. So, this was 1, 0, 0, this was 0, 0, 0, 1, 0, and this was 0, 0, 1 on number 8. Thank you. Beautiful. It's an equilateral triangle, and the L side of that equilateral triangle is square root of 2. And I even taught you how to cheat. That's why I was mad. I mean, I taught you how to cheat, and you didn't take advantage, right? So the area was L squared, square root of 3 over 4, which we did this together, like in 5th, 6th grade, by multiplying the height and the base and divide by 2. And then we came up with this formula with the Pythagorean theorem in the classroom. If L is root 2, you can very quickly get an answer. So that's going to be 2 root 2 over 4, which is root 3 over 2. And when I saw that people got something else except root 3 over 2, that broke my heart, really. But you have plenty of time to catch up for that in the final. All right? Did I expect you to really do the surface integral? Some people attempted to write integral over the shaded domain d of square root of f sub x squared plus f sub y squared plus 1 dx dy. That was the right track because this is root 3. And then the area, you get the area of the, this 1 times 1 over 2, right? 1 over 2 is the area. This root 3 gets out of this. So you have, when you integrate, you have the area of the shaded base, which is a half, and you get the same answer. No matter how you do it with calculus or without calculus, you still get it fast. Am I mad if you didn't do it, if you didn't get the answer? No, absolutely. But it hurts me as if, I don't know, a relative of mine messed up some task. That's why it's better that you don't know your students, because once you know your students, you know that they could have done better because you know them. So you say, okay, it really hurts when you know that they messed up, not because they are not smart or educated, but because they just either didn't pay attention or they were stressed out. However, my substitute, the guy who came here, was my PhD student. He got the doctoral degree in mathematics with me last year. And he told me, you were not stressed out at all. And I said, thank God. I'm glad that they were calm, and he said, I didn't look at the exam, but it seemed that they did very well and they were confident. And I was so happy. I was in Athens, Georgia, and reading this email, I said, yay, everybody's going to get an A. So I come home and I start grading, and I was sad to see that my prediction was not correct. But anyway, even with an average of B for an honors class, it's okay. I just expected a lot better. And I know it's going to be a lot better in the final. Number 9. This was done by almost everybody, except for a few people who messed up on the limits. I don't know why. When they drew x squared and they drew square root of x. And of course, you were supposed, the answer was 0 to 1, integral of. Now, if you do first x, you have x from y squared to square root y. Are you guys with me? Because this is smaller than that. Okay, so you have 1 dx dy equals to integral from 0 to 1, integral x squared to square root of x 1 dy dx. Now, what few people did, and I just forgave them. They just one put this like that, and here he put root 2 root y and y squared. Don't do that. It's like saying that a positive number equals a negative number, which is all complete nonsense. So the correct answer was with y squared down and square root of y, because this guy is bigger than this guy for something between 0 and 1. As I told you, square root of 0.04 is bigger than the square of that. Okay. Now, am I happy with that? I'm quite happy. In general, people understood the vertical strip method compared to the horizontal strip method. And why am I happy? Because I was asked by 3 people from other classes to help them over there on the corridor. And I asked them, who is your teacher, this and that. But we did not understand reversing the order of integration in class. I said, how come? Well, they didn't explain it very well. So I started explaining it to them, and then I realized that it's a conflict of interest. I'm not allowed to do that. And then I go, oh my God, I cannot do the homework for you. I'm not allowed. But I was already talking. So I said, guys, can you do it? I don't know. I said, yeah, do you draw? Why would we draw? They didn't teach us how to draw. I said, but how do you know about vertical strips and horizontal strips? No. And how do you do this? We don't know. We thought like we had to figure it out. Without drawing, without understanding how the vertical strips are drawn between 2 functions and how you switch to the horizontal strips, you cannot do this problem, period. So if you don't have, maybe some people have enough imagination, but that's very rare, that they can close their eyes and they can see a picture with their eyes closed and they can solve that, but that's not the way to learn. The way to learn is a very visual learning thing. Okay, so that's why we draw all the time.
Professor, you can cheat using Cal 2.
Yes, you can do that with Cal 2. What's the problem? You have integral from 0 to 1, square root of y minus y squared. Well, they learn to do the other one, right? The one with square root x minus x squared, 0, 1, and so on. But they were told explicitly to write. The professor even left these empty and put spaces, fill in the spaces, and they say, how the heck do we fill in those spaces? Plus the web work problems had the empty spaces, and they couldn't figure it out at all. And one of them went to the tutoring center and was lucky, because he got, this is like when you go to a medical doctor, sometimes you're lucky and get a good doctor who takes care of you, figures out what your problem is, and sometimes they give you the wrong medicine, okay? So one of them got the right tutor who knew how to explain and sort of knew something, but the other one got a tutor who never took Calculus 3 and said, I don't know what the heck these multiple snakes are, so I'm not gonna be able to help you. So he was very disappointed. Okay, compute the area of the domain D from the previous problem. This was something that nobody's telling you, hey, you have to do it with the double snakes. You can do it just with the simple snake and you're still fine. So in Calc 1, this is Calc 1, whatever it is. In Calc 1, you learn that you have to integrate this and you get 2/3 x to the 3/2 minus 1/3 x cubed at x equals 1 minus whatever. You have a 0, but at 0 you have 0, so you say forget about it. And you have 2/3 minus 1/3 equals 1/3, then you're done. Okay? Did I expect you to show me work? No. For everybody who wrote 1/3, and there were many people who did this mentally, and they came up with 1/3, they got 100%, I mean, they got 10 points on the problem. Finally, number 11, without computing the volume inside the sphere, x squared plus y squared plus z squared equals 2. Set up a triple integral corresponding to it in the space provided below. Some people, a few people, messed up. They forgot the Jacobian, so they put a 1 instead of r squared sine phi. When you work in spherical coordinates, they did fine setting up the limits, but they put 1 here. Don't do that in the final. You can ruin your lives this way. So you have r squared sine phi. Phi was the latitude from the North Pole. Here, it doesn't matter in which order you do it, but I would do it dr divided theta. You tell me what the endpoints are, and we are done.
0 to 2 pi.
0 to
No, the first one.
0 to
dr, it's the square root of 2. And d theta.
0 to pi, and theta all around.
2 pi.
Longitude 360 meridian degrees. Okay, 0 to 2 pi. So, good. So we are done. Did I expect you to write it down? No. I had 3 people who were nice and wrote down 4. I mean, they actually did the work. Maybe they had nothing better to do. I have no idea why. 4 pi r cubed over 3, right? And then they proved the formula in general using the Jacobian, using the formula. They got the correct formula for r equals square root of 2, and I was very happy. But did I ask you to do that? No. Did I give you credit, extra credit? No. So all the extra credit was just one problem to ask to do exactly what you were told to do. I don't know about how you feel about this exam, but it wasn't a hard exam. It was not an easy exam. It was an exam that was supposed to test what you learned until now all through the course. And that was the whole idea. I think you've learned very much, and I think you did fine, the majority of you, and that should ease the pressure on you when it comes to preparing for the final. I was thinking last night, I'm gonna send you probably by email or in person in class 2 or 3 samples of a final from the old finals that inspired us when we write the final. A few of us will provide problems and comments and suggestions when we write up the departmental final. The final will be departmental for all the sections. I don't expect more than 15 problems on the final. I have yet to think and decide if I want to follow the same policy. I mean, the final is the same for everybody, but the policy, about how to keep partial credit or not keep partial credit is up to us. And I already decided that I'm going to read everything. So in case that you mess up at the end with your numerical answer, you still get partial credit for your integrals or whatever you're showing. Also, one of those 15 problems might be for extra credit. I have to think a little bit better what is the maximum weight I want to put. But I would say, since I never reopen a homework and I never curve exams, I would think I could make 110% as the possible maximum. In this case, you have some cushion to make a mistake or two and still get a perfect score. Okay, I'm gonna move on to a new chapter. I have actually moved on already, but nobody believed me. Last time I started chapter 13. Chapter 13 is a mix of mathematics and physics. You'll be surprised how many things are coming from solid mechanics, fluid mechanics. It's Reagan. For a job? You want me to come with you?
Because I tried to talk to you up there.
Yes, yes. Yes. Yeah. You have to sign up, start the sheet, attend the sheet, and sign your name, and good luck with the interview. You should have told me before. I could have said a prayer for you. These things are very stressful. I remember my own interviews. There were several I didn't know anything about, and my hands are all sweaty. And you should never shake hands with somebody when your hands are sweaty. You have to do like this first, and be confident and don't be nervous, don't sweat or anything, because they can see that. All right, you just be yourself. Do you have earrings? Because after my several job interviews, those are good earrings, I was told that I should never wear dangling earrings at the interviews, which I did not because I didn't have any, but I love dangling earrings. And I was asking some academics why those are a problem. And they say they are distracting because mathematicians are like cats. So they look at the pendulum and then they get hypnotized by the dangling. So I don't know, I think most of the interviewers have some problems and they find some things distracting or annoying. So yeah, otherwise I think you are fine, just fine for an interview. Okay, so now serious job. We have to remember some of the things we don't remember, which are the gradient for a function of, let's say 3 variables. Let's grow up a little bit. And that was what? The vector field f sub xi plus f sub yj plus f sub zk, right? At an arbitrary point xyz in your domain, so where xyz is in some domain, you are in a potato, and the meaning of the gradient, the geometric meaning of this doesn't look like a potato, but it's some sort of solid that it corresponds to a closed surface, and this closed surface that closes up in itself is having a hard time now. It has a normal, and this normal is given by the gradient of this function written implicitly like that. You remember that, and that was a long time ago, but you should still master that. Last time I gave you the z equals f of xy, z equals little f of xy as a graph of a function of 2 variables over a domain in plane. We computed the gradient of that, but that's what we did all through the midterm. So that's no fun. I mean, we know that too well. On this problem, I gave you some new piece of information last time. So I said, if you have a vector field that looks f1i plus f2j plus f3k, where fi is C1 that means it's differentiable and the derivatives are continuous. What was the divergence of f? Well, that was before the Easter break, and I know we had a long break. I cannot recover from this break so easily because it was long, and I also traveled last week. But before I traveled, I remember that I gave you this, and you memorized it. Most of you memorized it. How was it? The first component differentiated with respect to the first variable, plus the second component differentiated with respect to the second variable, plus the third component differentiated with respect to the third variable. So I'm asking you as an exercise, like I did last time, the same thing. Exercise 1 for this section. Compute divergence of the gradient of f, where f is a function, C1 function of x, y, z. That means f is differentiable and with continuous derivatives. What does it mean? It means that you have to compute divergence of f sub xi plus f sub yj plus f sub zk. And you're thinking, I can do that. By definition, I take the first component. Who was that?
Ryan.
Oh, right. I thought that somebody wanted to come in, and then he heard me and he changed his mind. F sub x prime with respect to x plus F sub, like when you go on a blind date and you see change your mind. Okay. F sub y plus F sub z. Do you remember that I gave away 95 cents for this type of question? So what was this operator? We can write it better. We can write it using the second partial derivatives with respect to x, y, and z. And we gave a name to this one. We call these names Laplace operator, Laplacian. That's how you spell it, Laplacian. Okay. Of f, and then what do you have? You have to introduce a new notation, and when you see this triangle that looks like an equilateral triangle, this means Laplacian of something. So if you have a function of two variables, let's say z equals f of x, y, what is the Laplacian of this little f? Little f xx plus little f y. So it would be the second partial with respect to x plus the second partial with respect to y. What if I have something else, like, let me give you a more general function. Let's say I have a differentiable function of n variables with continuous derivatives, and it looks like crazy. It looks like that. x1, x2, xn minus 1. Well, the Laplace operator in this case will be f sub x1, x1 plus f sub x2, x2, which means the partial of f, the second derivative with respect to x2, and plus the last derivative twice with respect to the same variable. And the last variable is xn minus 1. So this would be 1,000,001. I don't know why. You can have as many variables as you want. Now, actually in engineering, there are functions that have many parameters. You have 3 spatial coordinates, then you have time, then you have temperature, then you have pressure, then you have God knows what. The surface tension of the membrane, and many things. You rarely have 1,000,000 parameters. Actually, it's impossible. It's even hard to work with 10 parameters. Imagine always working with equations that have lots of variables and having to deal with them. In fluid flows, hydrodynamical problems, most of the time in 3D turbulent flows, for example, then you have X, Y, Z spatial coordinates and time, T. So even with 4 variables, what you get those operators, you could have something like F sub X, 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 T plus G sub X, X, T plus and so on, all sorts of ugly components. Sometimes you have equations of fluid flows in dynamics of fluids. Fluid flows with turbulence are really a area of mathematics in itself. You have really complicated equations with most of the operators. I was looking at them in Georgia when I went to this conference. Most of those equations were order 4. Of course, most of them you cannot even think about solving by hand or with any known methods. You can solve them numerically with computational software. That is the only chance that mathematics, modern mathematics, has in some areas right now. Write software in order to find solutions to a fluid flow with turbulence that is a solution to this type of equation, like Navier-Stokes, for example, now. Now, we are going to see, you are going to see, I'm too old, I saw that 20 years ago. When you go in 3350 ODE differential equations, and then if you do PD 3351 in engineering, you're going to see lots of equations that are hard to solve. But in many of them, you're going to see partials like that. And you're going to say, oh, thank God that I like partials in Cal 3, so they became my friends, and you will never have headaches in ODEs if you understood the notion of differential very well, the notion of partial derivatives very well. Okay, so I'm gonna erase this one. Okay, and then I'll say, I don't know how many of you, I'll try to make this formula more visible. Some of you maybe who are engineering majors know about curl. Have you heard about curl? Curl of a vector value function? No, you haven't. Okay, suppose that you have a vector value function that is f of coordinates x, y, z, 3 coordinates, and C1 over a certain domain, omega. Omega is the domain that your spatial coordinates live in. X, y, z live in some potato, let's say. A solid body enclosed by a closed surface. In that potato, f is a differentiable function with respect to x, y, z, and the derivatives are continuous. Now, in most cases, if you work with Laplacian, this is not enough C1. If you work with Laplacian, what do you need? You have f sub xx plus f sub y1. So you need C2. You work with at least C2. Many examples have C infinity. That means you're having really beautiful functions that are elementary, some of them even polynomial approximations. And then you really can differentiate them ad infinitum, and all the derivatives are continuous. And then you can call yourself lucky. How do you introduce the notion of curl of f? And it sounds funny, and this is why they made this pun. And I used to be curly, but I straightened my hair over the holiday, and now it's between. So curl of f is something that looks horrible when you try to memorize it. So you say, okay, if I'm going to get this on the final, you better wear this t-shirt. So no, that's not that. There is something better than that. One time I was wearing, okay, my students got no permission from the course coordinator to come with a cheat sheet. But I was wearing a t-shirt that had Green's theorem. I don't know how many of you have heard about Green's theorem. We are going to learn it in 2 weeks. And I was wearing that t-shirt. And so one student, and it was by accident. okay? I didn't do it on purpose to help my students cheat. So one student at some point goes like, well, I don't remember Green's theorem. Then he looked at my t-shirt. Oh, all right, never mind. So he had Green's theorem on my shirt, and I was saying, well, that was a good idea. But it's hard to wear like 10 t-shirts. I have one for the formula of the curvature of a curving space. Remember that one?
Yeah.
That is so nasty. Okay, I have this one. I have Green's theorem. I have Stokes' theorem. All the important formulas, actually. I have 10 t-shirts. And then I was thinking, how would I be if I were like taking 10 t-shirts on top of the other and taking that one off at a time during the final? There is no cheat sheet. There are no formula sheets, no nothing. I would look like Joey from Friends. Remember Joey when he was dressed in many layers? So, rather than that, I'd say, ask me. Say, oh, you know, I'm freaking out. I'm taking this final, and I forgot curl. Rather than not attempting a complex problem at all, ask me before the exam, and I will remind everybody how to set up the curl formula. So you simply have to think in terms of operators, ddx, ddy, ddz. What are these? These are the derivative operators. So you think, if you put this, if you take this and multiply by a function, that means df dx, formally written. All right, so in this case, if f is, I'll put on my t-shirt, pi plus qj plus rk, where p, q, and r are all scalar functions of x, y, z.
Then we will not forget it.
Then we are not going to forget it, and you're not going to need my t-shirt. All right. So how do you do that? You go expand along the first row. I times whoever the minor will be, which is this guy. How do you do? The cowboy problem, these guys multiply each other. So you go dr dy plus or minus dq dz close times I. So the I is the corresponding element to the minor that I just computed. This minor is the determinant, which is exactly this guy. And this is exactly what my t-shirt says. Right, precisely. Okay. The second term, did they put the minus? No, they changed the signs. That's a pain. I would put minus because I'm expanding along the first row, that means second element, minus something minor times j. Which minor? Let me make it in all in lime. Lime is a nice color. And then I'll take this, and that. dr dx shooting cowboys, diagonal, minus dp dz. And of course they wrote dp dz minus dr dx. So I would leave it like that, it doesn't matter. You can put the minus in if you want. Plus the k guy. K goes at the end. The k goes at the end. And then k multiplies this determinant, dq dx minus dp dy. dq dx minus dp dy. Okay. Is it hard? No, it's not going to be hard to memorize. So again, how did we do that? We set up the first row to be ijk, the second row to be ddx, ddy, dz, and then all in order the components of your vector value function in the exact order they are with respect to the standard basis ijk. All right. Now, there are other names and other symbols for curl of f. They use curl because it's in English. Well, actually, in Great Britain, I saw that they use rot. Also, they use both. In my language, in Romanian, we call it rotor, and I saw that in French, it's very similar. They use the same. Now, in the mechanical engineering notation, it's funny. They use a nabla symbol and a cross product symbol F. And by that, they mean curl F. Okay? So if you talk to a professors in mechanical engineering or fluid mechanics or something, they will, when they talk about curl, they will use this notation. When they use this other notation, what do you think this is again? Divergence, yes, I told you last time. That's divergence of F. So make the distinction between, Regan, when are you leaving? Huh? Okay, so you have plenty, you're not gonna miss one. And then we have this distinction you use here like a dot product and you use here as a cross product. Now, you have to understand the difference, the conceptual difference is huge between these guys. This is a scalar function, this is a vector function. Vector, scalar, vector, scalar, vector, scalar, vector, scalar. Okay? Because I've had students who may mix them up and I heard of colleagues complaining in the final, while grading the final, that the students did not understand that this is a vector and this is a scalar. Okay, a few simple exercises. I'm going to go ahead and do some of them. We try to make the data on the final exam very accessible, very easy to apply in problems. And one of the problems that we start with example 2 would be this one. And you may think, why? Sometimes we put it in disguise. And we said, assume you have a sphere. That's the unit sphere of origin O. And say, compute. What is the equation of the unit sphere, guys? X squared plus y squared plus z squared equals 1, right? Compute F equals normal, external normal to the unit sphere pointing out. Prove that n is the same at a different point as the position vector. Then compute the following. Gradient of f, divergence of f, and curl of f. Now that should be a piece of cake. But what is not so much of a piece of cake, if you don't understand what the problem wants from you, is to actually get the expression of this normal. So you're going to say, what is the normal to a function like that? First of all, we just talked today about it. If you have a function given implicitly as f of x, y, z equals to c, in that case, n is your friend from the past, if it's a unit normal to a surface, happens all the time in engineering, whether you do solid mechanics or fluid mechanics, you always have to complete these things. This is going to be what? The gradient of f divided by the length of the, but here I have a problem, I have to put g here, because g will be my position vector. This is the point x, y, z. Would you prefer big R? But I think I prefer big G, because big R looks like a scalar radius, and I don't like that. So the position vector would be the sort of needle that starts at the origin and whose end is on the surface, right? And this is the equation, xi plus yj plus zk. What? Because my point x, y, z has a corresponding vector xi plus yj plus zk. Big deal. Now I'm trying to convince you that for the unit normal for the sphere, I'll have the same kind of thing. So how do we compute this normal? I take the function f that implicitly defines the surface. All right, so in my case, f is something else. Is what is it? X squared plus y squared plus z squared. Let's compute n. N is gonna be, I believe no, it's very nice. 2x, comma 2y, comma 2z, divided by the square root of the sums. Do I like this? No, but I'll have to do it whether I like it or not. I want to simplify up and down by a 2. Can I do that? Of course I can. I'm going to get xyz divided by square root of x squared plus y squared plus z squared. And this is 1.
Would still be 2 though, because it's 2 squared, so it's 4.
No, I pulled it up.
Square
That's
root of
exactly what I said. There was a 4 inside. I pulled that with the forceps, I put it up here, square root of 4. And I have a 2 here, and that cancels out. So I got something much simpler than you guys expected at first. I got xi plus yj plus zk as being the normal. Did you expect this? Well, you were supposed to expect that this is y, because this is the position vector and has what length? The length of the blue vector is 1, and the point is on the sphere. The normal will be exactly the continuation. Take your blue vector and continue in the same direction. That's the beauty of the normal to a surface, that it continues the radius. It continues the radius of the sphere in the same direction. So you copy and paste your vector, your position vector g will be the same as the normal n. All you do is you shift, but it's the same vector. At a different point, it starts at, instead of starting at O, it starts at P. So what? It's the same vector. So you take the radius vector from inside the sphere, position vector, and you shift it up, and that's the normal to the sphere. So its equation is still xi plus yj plus zk. Yes, sir?
Does it remain the same for any of the functions? Like every time you write normal would be equal to the position vector?
For the unit sphere, yes it is, but for a general sphere, no. For example, what if my sphere will be a center origin and radius r?
5.
Then the position vector is x, y, z, like that. This I don't know, g, right? That's position vector.
But you just divide them by the R, right?
You just divide by the r.
Yeah.
So instead of radius being big R, your unit vector will be this one. And you take this one and shift it here, and that's all you have. For the sphere, it's beautiful. For any surface in general, no. Let me show you. You have a patch of a valley, and your position vectors look like crazies, like that. And the normals could be, they don't have to continue the position. They could be, it depends how the tangent planes look like. And the tangent plane at the point has to be, you see, has to be perpendicular to the normal. So the normal field is the end green vectors. The little thingies that look like rectangles, whatever they are, those are the tangent planes at those points. So in general, there is no obvious relationship between the position and the normal to the surface. You are really lucky for the sphere. And for many reasons, like how beautiful the sphere is, these functions will be easy to compute. Can you tell me what they are without computing? Because that should be a piece of cake. What is the gradient field?
The gradient for that one? What's the x, y, and z?
For the sphere.
2x, 2y.
Actually, let's do it for both gradient g, gradient divergence g, and curl g. And you say, wait, they will be, so gradient, no, I meant here you don't have gradient, okay? When f is a scalar function, then you have gradient.
Yeah.
Then for that gradient, you're going to have divergence, and for that, I changed notations, that's why I have to fix it. Because f used to be that, and it's not a vector anymore. So big F is not a vector anymore, it's a scalar function, and now I have to change the problem. And I want, what is the gradient of f? What's divergence of the gradient of f? What's curl of gradient of f? And for the g that I gave you, I want the divergence and the curl. So I made the problem fluffier than it was before. More things to compute for practice. What's the gradient? We did it before, 2x, 2y, 2z, where at an arbitrary point P on the sphere, it could be anywhere in space. What's the divergence of this individual? So remember guys what I told you? First component differentiated with respect to x plus second component differentiated with respect to y plus third component differentiated with respect to z. 2 plus 2 plus 2 equals 6. Piece of cake. And curl of gradient of f. Is that hard? No, but we have to know the definition, and we are, without looking at the t-shirt, how do we do that? Curl it. Determine ijk, operators ddx, ddy, ddz,
and it's 2x, 2y, 2z, correct?
and we copy and paste the three components. This goes in the trash. I'll take the blue, so you put 2x, 2y, 2z. Do you think it's going to be easy or hard? Do you see the answer? Some of you are very sharp and they see the answer. For example, when the cowboys shoot at each other like this, dz dy is 0. dy dz is 0. So this as a minor is 0. 0i. An I for an I. And what else? dz dx, dx dz, same thing. Minus 0j. Is it silly of me to say minus 0j? Yes, it is, but I did it because I want you to have the good habit of saying plus minus plus. And plus finally, the same kind of thing will give you 0k if you think that when you do partial derivative of y with respect to x, you get 0, you have 0. So some student of mine asked me, so this is the 0 vector. How in the world do I write the 0 vector on short? Let me show you how. You're going to laugh at me. Some people write 0 bar, which means the 0 vector. Some other people, I don't like it, it's silly. Some people write O with double like that, meaning that, hey, this is a vector element, the vector whose components are 0, 0, 0, to distinguish that vector from the number 0, which is not in bold. So, the notations for the vector 0. So I'm going to write here 0, 0, 0. How about Mr. G? Mr. G will react similarly. When you do the divergence, it's going to be 1
1, 1, 1.
plus 1 plus 1 equals 3. You should remember this thing. We are going to do the divergence theorem, and in the divergence theorem they will ask you to do a triple integral of a divergence of a vector field. And when you do that, you are going to get a triple integral of something like 3, which is a constant, which will make your life very easy. So you will very easily compute those triple integrals of constants. Curl of G, G being a vector, okay? I should make the distinction between a scalar function and a vector function by putting a G bar on the vector function. How about this? Is it hard? Nah, it's the same fellow. Instead of that, I have just x, y, z. The answer will be the same. So I'm still going to get 0, 0, 0. The vector 0. So the problems that we will give you are not, you may expect them to be very hard, but they're not going to be very hard. Let's do one more, like the ones we have in the book. What do you think this one will be? Let me give you a new vector valued function. That's funny. Maybe 2 little exercises because you're just working. Exercise 3, 4, I don't know what they are. Let me give you R vector of x, y, z equals yzi plus xzj plus xyk. Compute the curl. Let me write it like engineers do, or just for fun. Nabla cross R, which is the same as curl R, which is ijk. Oh my God, ddx, ddy, ddz, yz, xz, xy. And you say, oh, that's not so easy anymore. You will see that it becomes easy, okay? I times what is the minor? This, x, right? Minus x plus minus j times what minus what? The minor will be the red thingy. And the red thingy is beautiful because it's going to be y minus y plus k times, who do you think it's going to be? Z minus. So it's still 0. Do expect something like that on the finding. An easy computation, somebody says, find me the curl of this function. And the functions usually we give you are nice and symmetric and something where the result will be pretty. Okay. Let me see what else I wanted. I'm gonna, I have space here. So compute the curl and Laplace operator, the Laplace operator of f of x, y, z equals x squared yz I plus xy squared zj plus xyz squared k. A divergence. Sorry guys, it's not a scalar function. I want the divergence and the curve. The curve will be a vector, the divergence will be a scalar function. Later on I'll give you a nice function where you can compute the Laplace operator that's going to have to be a scalar function. And although the Laplace operator can be generalized to vector functions, and I'll tell you later what that is. It's very easy. It's practically the Laplace operators in every direction. Okay, so let's see the curl. Ijk ddx ddy ddz. Today I'm going to cook up the homework, and with all the practice that we are doing now, you should have absolutely no problem doing the homework for the first two sections, at least for the section, today's section, 13.1. X squared yz, xy squared z, xyz squared. You see there is some sort of symmetry. I'm playing a game here. So I have I want you to tell me now. You see now I don't work much in groups. I don't make you work in groups, but I want you to answer my question. So what is going to be this minor that the first thing is going to be
xz squared
very good
minus
xy squared minus j. Attention at the minus, okay? What is the next guy? yz squared, thank you. X squared, right? Plus k times y squared z. So, you see what I'm doing? I'm doing this prime with respect to x. Y squared z, you said it right, minus this times x squared z. Can I write it more beautiful? I don't really like the way I wrote it, but I'll write like that. How about x times z squared minus y squared I minus j, or maybe better plus j, I'll change the sign, plus j at the end, because it's the vector, y times x squared minus z squared, j, plus, who gets out? Z, okay, z times y squared minus x squared, okay. Okay, good. There is some symmetry in there. The breaking in symmetry is in the middle. Because, as you see, x is separate and then z is followed by y, and then x squared, x is followed by z, and y is followed by x. So I have some symmetry of some sort. What else did I want? Divergence operator. And that will be the last example of the kind. Now you know more than you need. How do you write the divergence? Is this hard? Very easy. I'm going to ask you to simplify because I don't like it like as a sum. 2xyz
2xyz plus 2xyz plus 2x.
And now you see why I don't like it as a sum. Because it's 6xyz and it's very pretty like that. I'd like you, on the exam, I'd like you to take the function and box the answer, and that's all I wanted to do. All right, I'm going to go ahead and erase. going to move on to 13.2, but I'd like to review some physics a little bit with you. Let's see what you remember on physics. It's a little bit messy. I'll use this instead because I like the board to be clean. If I were to ask you to remember work in physics, I would say I'm changing a little bit the order in 13.2. I'd like you to go back in time and see what work was in your physics class.
Force over time.
No.
Force square of force dx.
What if you didn't know any calculus? Let's go a long time ago. Section 13.2, preliminaries.
Force multiplied distance.
Very good. Preliminary work. Preliminary work is work. The notion of work from physics. Hey, come on.
F dx.
Physics or engineering, mechanics, whatever you studied, work. Imagine that you are taking this is your body that you play with. It is not your own body, but the body you're acting on in physics. And you're dragging this object from a place A to a place B, another position. AB is the distance. And the force is parallel to the trajectory. This is very important. This is a simpler case. In general, it's not so simple. So this force is acting, and it's a constant force, and you pull the object from one place to another. That's case one. In case two, life is harder. You actually pull the poor object with a force in this direction. Actually, most of us do that, right? If I were to have a gliding object on the surface, I would actually act on that object in the direction of my arm by pulling it. So when I displace this body from point A to point B, I still travel the distance d, but so d is a displacement vector that can be written like, can be drawn like that. I have to be smart in both cases, figure out what I want from life because it's not so clear. When they taught me, I think the first time I was in, oh my God, 8th grade, 9th grade, that was a long time ago. In this case, W is going to be a scalar, and I'm going to have the magnitude of the force F. F is a vector, but to indicate it in newtons or whatever I measure it, it's going to be in magnitude. Times the little d, but instead of little d, I should be a little bit smarter and say, Magdalena, this is the magnitude of the vector AB, which is a displacement vector. So this is called work. And if the force is 10 newtons and the distance is 10 meters, because we want to go international, we want to be global, right? At Texas Tech, so good. So we have 100 Newton meters. Now you can measure, well, you can have another example, thinking gravity, and then you can say it in pounds, and that measures force, and you have other units that are not international. I'm not going to mess up with it. When you have the work, in this case though, it's more complicated. And I'm not going to be mad at Unity, she's trying to tell me what it is. I'm not gonna be mad at the people who don't know what the work is in this case, although I was looking at, well, I am the person who has run a committee to oversee the finals for different math classes, all the math classes we offer. And every semester I see the trig, pre-calculus, calc 1, calc 2, calc 3. In trig and pre-calculus they always have a work there. And I was wondering how many of you took pre-calculus and how many of you remember that you studied this in pre-calculus. It's a little bit awkward. I'm thinking, how do they do it? But they gave you the formula and they say the force in itself as a vector, dot product the displacement vector. So they are both forces in dot product. And I was surprised to see it, that they gave it to you. If I were to express it, how would I express it? I'll say the magnitude of F, of course, in newtons, whatever it is, times the magnitude of the displacement vector,
Multiply those cosine
cosine of the angle
between them.
between, and I'm too lazy, I don't know, theta, let's call it angle theta, because I don't want to include other notations. Okay. It really doesn't matter in which direction I'm going, because cosine theta, thank God, is an even function, is equal to cosine of minus theta, so whether I go this way or that way is the same cosine. All right, so the cosine of the angle between the two. It's very easy when you don't need calculus. But when you use calculus, because your trajectory is no longer a line, life is becoming more complicated. So we have to come up with a different formula, with a different notion of work. I'm gonna erase. Are you guys done with that? Is it visible? You're done. Okay. So again, life is not so easy in reality anymore. I have a particle in physics. A photon enters a 4-star hotel and says, talks to the bellboy. And the bellboy, can I help you with your luggage? No, I'm traveling light. So the particle, the photon, whatever, a particle is moving on a trajectory. Suppose that trajectory is planar, just to make your life easier at first. It's in the plane xy. And this is the little particle that's moving. And this is r, and that is xi plus yj. Good. And this is the point xy. And that's the position, the current position of my particle. Where now? Not in the past, not in the future. My particle is moving, and this is now. Suppose time doesn't even exist. We think of the movies that we saw lately, and the theory of everything, whatever. So then we say, okay, we only care about now. xy is now, and that is the current position vector. Well, what would be the work between now, whatever now, and the next, let's say this is gonna be x1, y1, and this is x0, y0. That's, the general formula will be xi plus yj. So I actually cannot forget about time. Not as much as I want. So x and y are both changing in time. I'm going to have x equals x of t, y equals y of t. Do you guys remember what we called that kind of equation for a curve from here to here? Parametrization or parametric equation. parametric equations. Good. So I have, may the force be with thee. I have a force. And I have some sort of displacement, but I cannot express that displacement linearly anymore. I'm moving along an arc of a curve. So I have to think differently. Then the work will be defined, whether you like it or not, as if vector field dot product with dr over C. And you say, what in the world is that? What would C be? How do I integrate along a path? And I will tell you in a second what we mean by that. Meaning that, this is by definition if you want, this is like an application of Calculus 1. It can be proved. We do a rigorous job in the book about introducing and proving that along a curvilinear path. This is going to be, where am I here? At time t0? And this is at time t1. That means x0 is x of t0, y0 is y of t0, and at the finish point, I'm at x1, which is x of t1, and y1 equals y of ty. So between t0 and t1, I have traveled, and I have, if we're measured at x of t, y of t, where t is moving between t0 and t1, I'm done with this is the f part. What is the dr? Now you guys know about differential. Thank God you know about differential, because this is going to help you very much. Okay, so instead of dr, I'm going to write dot, and let's see how I write, what I write in terms of dr. You may say, well, what does she mean? dr was dxi plus dyj. And you say, why is that? I don't understand. Because r itself is xi plus yj. And x is a function of t, and y is a function of t. And that means that when you apply the differential, you are going to apply the differentials to dx and dy, and these are going to be infinitesimal displacement. Infinitesimal displacement. Infinitesimal displacement. What is an infinitesimal displacement in terms of time? Well, we have our parametric equation. So Mr. dx as a differential is that just x prime dt is like in the u substitution. dy is just y prime dt. So let me write this down again. This is x prime of t I plus y prime of t j times dt. So Mr. dt is like a common factor. He wants to go out for a walk. He says, I'm going to go out for a walk. I'll go out for a walk. So dr is actually x prime of t times I plus y prime of t times j dt. And this will represent the derivative of r with respect to time. So that will be what? The differential of r with respect to time. Okay, this is the same as writing dxi plus dyj. And is the same as writing dr. Why is this happening? Because it's it's a chain rule because x and y themselves are functions of one variable only, which is time. This is why it happens. Oh, so we will simply have to do, to learn new things, right? We are going to have to learn new things like integral from a time, fixed time, 0 to t1, which is 10 seconds of the dot product between a certain vector that depends on time and another vector that depends on time, and dt. So we are going to have to learn how to compute the work through this type of curvilinear integral. And this is called either path integral along the curve C, or curvilinear integral along C. Yes.
Let's say if I knew the force, this is given to us in function, right? So I can find arc length that is between x
Yeah,
from one point to another point.
yeah, we will do the one with arc length next time. There is also,
Is it harder?
no, you can pass to arc length, and we'll do that next time. You will have an integral with respect to s, so the integration will be with respect to ds, the arc length. And then you will have a function that depends on s.
Yes.
So for today I only teach you that. Next time I'll teach you that with respect to arc length, which is also is not hard at all. So I will work with you on some things. Now, assume that we have, I will spray all this thing. Assume that I have a problem. I have a parabola, arc of a parabola, right? Between, let's say the parabola is y equals x squared. Between 2 points. And I'll ask you to compute some work, and I'll tell you in a second what you need to do. So, exercise 2. Assume the parabola y equals x squared. Between points A of coordinate 0, 0 and point B of coordinate y 1, 1. A, parameterize this parabola in the simplest way you can. In the simplest way you can. And B, compute the work along this arc of a parabola, arc AB of this parabola, performed by the function big F of t. You see that I'm going to say no, big F of the point xy, because you haven't parameterized that yet. Big F of xy being xi plus yj. So you say, oh, okay, wait a minute, W will be integral over the arc of a parabola. Do you want to draw that first? Yes, I will draw that first. So I have this parabola from A to B. A is of coordinate 0, 0. B is of coordinate 1, 1. And this is y equals x squared. So what kind of parametrization is the simplest one? The regular one that people take x to be t, and of course take y. In that case, y will be t squared. And for 1 you have 1, for 0 you have 0. When you write that word by definition, what was that? It was written as integral along the path C. Let's call this path C a curvilinear path, look, script C. So beautiful. Let me make it in red and draw the C. Of what is work? F force, may the force be with us, dot dr. dr. Alrighty, that's a little bit of a headache. This F is going to be, can I write an alternative formula that I have not written yet, but I will write in a second. dr will be dxi plus dyj. So I can also write that f dot dr as a dot product will simply be, what was the dot product, guys? Do you remember? First component times first component, f1 dx, plus second scalar component times second scalar component, f2 dy. I'll write it down. Along the path C, I'll have f1 dx plus f2 dy, but God knows what it's going to be in terms of time. So I have to change variable thinking. Okie dokie, Mr. dx by substitution was x prime dt. Mr. dy by substitution was y prime dt. So I'd rather write this in a simpler way. This is a new object, path integral, but we know this object from Calc 1 as being a simple integral from time t0, I'll write it down, to time t1, f1 x prime of t plus f2 y prime of t. This is the integrand dt. This should be a piece of cake, right? For us to apply in this problem. Equals. Now you tell me what I'm supposed to write, because if you don't, I'm going to not write anything. T0 for me is what time? When did we leave this? 0. And when did we arrive? At 1 o'clock. I arrived when t is 1. Whatever it is, 1 second or whatever. Depending on our particle. Okay. From 0 to 1. Now, who is F1? F1 is x, but it drives me crazy because I need this to be expressed in t. So I think of x and y as functions of t. So f1 is not x, that I'm going to write here, but t, which is the same thing in parametrization. This is t. T times. Who is x prime of t? 1, thank God, that is easy, times 1 plus f2. Who is f2? T squared. I'll have to write it down. Times, who is y prime of t? 2t. Y prime is 2t. So I write it down, 2t. dt. So that's how I compute this integral path. Is it hard? No, because it's just a simple integral from calculus 1. So I have to integrate what function? A polynomial. 2t cubed plus t with respect to t between 0, time 0 and time 1. Good. Let's do it, because that's a piece of cake. 2 times t to the 4 over 4 plus t squared over 2. I take the whole thing between, I apply the fundamental theorem of calculus, and I have between t equals 1 up and t equals 0 down, what's the final answer? It's a simple final answer, and again, on the exam, on the final, do not expect a heavy computation. Do expect something simpler like that, where you don't need a calculator, you just have either integers only or simple fractions to add, and you should get the answer. What is the answer, guys? 1. 1/2 plus 1/2 equals 1. So 1 is the value of the work in what? Measured in newtons times meters, whatever your units are. When you drag the object from this point to this point, on which the acting force is the only acting force, which could be the resultant of several forces. That is that force that you have here. Is it useful? It's very useful for engineers. It's very useful for physicists. It's very useful for anybody who works in applied mathematics. This notion of work given like that. I'm going to go ahead and erase, and I'll ask you one thing here. That is not in the book, I think, as far as I remember. Can you guys prove that this sophisticated formula becomes your formula, the one you claimed, the first formula you gave me? Is it hard? Do you think it's hard to prove that this? Okay, what if we have the simplest possible case? Let's think of, yeah, I'm thinking maybe I should do, well, A to B, right? A, B. What kind of expression do I have in place? If I take this to be, I could have any line, right? I could have any line, but then if I have any line, I can pick my frame according to my preference, right? Nobody's going to tell me, well, you have to take a frame like that, and then your line will be of the form ax plus by equals. No, I'll just take the frame to be this one, where AB will be x-axis, and A will be a coordinate 0, 0, and B will be a coordinates B and 0, and this is just my line. So x will be moving between 0 and D, and y is 0. Right? It should be easy. And then f, let's say f should be this function, this and assume the angle is constant, just like I had it before, theta, and then it's acting all the way on your object. You have the same angle here all the way. So F is F1i plus F2j. The R will be dxi plus dyj. But then you say, wait a minute, but didn't you say, Magdalena, that you are along this line? Didn't you say that y is 0? So which y? So there is no y, so this is 0, right? Okay, Mr. X, I want to parameterize my trajectory. How do I parameterize it the simplest way? I'll take x to be t, and time will be exactly between 0 and d. And y will be 0. And thank you God, because that's easy. And so, all you need to give me is w is integral f dr c in that case. So what am I going to have in that case? I'll have this formula, right? I'll skip a step and I'll have that formula, and that means I have integral from t0 equals 0 to t1 equals d, F1, now you have to tell me who F1 will be. X prime of t is 1. The second guy is 0, thank you very much, and goodbye. F1 will be what? Well, life is nice. F1 will be the projection of the vector F on my x-axis. So F1 is the length of this blue vector, for God's sake. So F1 will be, F1 is a scalar. Let's say F1 is a scalar component. That means it's F length cosine theta, because it's like hypotenuse times cosine theta. So it's easy. So you have length of F, how much it is, how big this vector is, times cosine theta, times what? When you integrate it, guys, when you integrate 1 with respect to t, what do you get? T between d and 0. So you have t between d and 0. We got the formula. So we got that F length times magnitude of it times cosine theta times d. This is the displacement. This is the cosine. This is the magnitude of the force that I'm look, this is the force. My force is along my arm. I'm just dragging this poor object. But the force I'm acting with, suppose it's always the same parallel to that, I can feel it here. Okay? So that's what I have. F cosine theta d. It was this. So as a particular case of this nasty gram, of this nasty integral, I have my old work from school that I had to believe. I tell you guys, I did not believe a word, because my teacher in 8th grade came up with this out of nothing, and we were supposed to be good students preparing for a high school like this kind of scientific. Back home there are different kinds of high school. There is scientific high school with emphasis in math and physics. There is one for chemistry, biology, there is one for languages, linguistics, humanities, and so on. And I was for the math and physics one. And I had to swallow this formula without understanding it. And it took me many other years to understand that it's just a little piece of a big picture. And that there is something bigger than what we were taught in 8th grade. Alrighty.
We call them Lyceums.
Huh?
The school. Lyceums. So the name of
Yeah.
lean more to the math and physics.
Yeah. It's true. One of the next one. Now, I want to ask you a question. So, do you think that I would get any kind of conservation laws in physics that apply to calculus? I mean, how hard is it really to compute the work? And I'm making an announcement now, since I have not given you a break, I have to let you go in a few minutes. But I'm making a big announcement without proving this. So we will, in about 1 week maximum 1 week, we will study the independence of path of a work if that work is performed by a conservative force. And And you're going to say, wait a minute, what the heck is a conservative force and what does she mean? Well, I just showed you that the work is a path integral. We don't know what that is. I'll introduce more. I'll just introduce the definition of a path integral with respect to a parametrization, general parametrization with respect to t, so that becomes an integral with respect to dt, like the one in Calc 1. This is how you have to view it at first. But guys, if this force is not just any force, it's something magic. If F comes from a scalar potential, that is, F represents the gradient of a scalar function F. This is called scalar potential. Then F is called, now let's see how much money I have for just the last 2 or 3 minutes that I have left. I don't have money, I have money, but they are big money. No. I have $5, I was looking for $1. I give you 5, you give me 4 back. If you guess, I don't know. So maybe in your engineering courses, maybe I give you some candy instead.
Yes. Candy.
So, if there is a scalar function f of coordinates x, y, whatever you have in problem, so that big F will be the nabla F. Nabla F means the gradient. We say that F comes from a scalar potential, but it has also a name. F is called God. It starts with a C, ends with an E. In that case, if this is going to be equal to nabla F, in that case there is a magical theorem that I'm anticipating, I'm not proving, I'm not doing exercises right now. We'll see it in 2 sections. That the work does not depend on the path you are taking. So you can go from A to B like that, or you can go like this, you can go like this, you can go like that, you can go on a parabola, on a line, on anything. The result is always the same, and it's like the fundamental theorem of Calc 3 in plane for the work. So you have a little f of endpoint,
Is that called
f of origin. So all that matters is computing the scalar potential here and here, making the difference, and that will be your work. It's a magic thing. In mechanical engineering, maybe you met it in physics, in mechanical engineering, because that's where you guys drag all sorts of objects around. Rachel, you're a math major, I think. You're an engineering business major. Wow. Okay, who else said conservative? And were there other people who said conservative? I'm sorry I don't have, well, next time I'll bring a bunch of dollars and I'll start giving prizes as dollar bills, like I used to give in differential equations. Everybody was so happy in my class because for everything that they got quickly and right, they got $1. So conservative, very good. Remember that for the next few lessons, we will show that when this F is magical, that is conservative, you guys don't have to compute the integral at all. It's not, no parametrization, nothing. It really doesn't depend on what path you take. All you would need is to figure out who this little f will be, the scalar potential. I'll teach you how to do that. And then you compute the values of that scalar potential here and here, make the difference, and for sure you'll have such a problem in the final. So I'm just anticipating it because I want this to be absorbed onboarding time into your system. When we will do the final exam review, you should be doctors in this kind of problem, so that everybody will get 100% on that for the final. Okay, now I'll let you go. I'm sorry I didn't give you a break, but now I give you more time. And enjoy the day. I'll see you Thursday. I'm moving to my office. If you have questions, you can come to my office. Maybe you were getting close, but they, how did you know? Or it just came to you? That means you get a broad education. Not this time. I usually do, and I love to teach that, but I'll be the next chair of the department next year. So I did not expect this honor, but that means they will request my teaching load. I will tell you who. The board will see us, but it doesn't matter. David, he's the best in teaching freshman.
Do you know what section it's being? Because I don't even think he's like listed or anything.
Send me an email if you don't figure it out. But for sure you will teach 3350.
Okay, because I was going to do the
He's
honors,
extremely good.
but it was Lourdes, so I don't know if he's good or she's good.
He's good, but he's fantastic in the sense that he will help you whenever you stumble. He's an extremely good teacher. He explains really well. He has a talent. He's a talented instructor.
Okay, I'll look for him. Thank you.
Okay, and if you don't get with she is good as well. Not exceptional like he is. He's an exceptional teacher.
Okay.
I'll go to the office.
Yes. Yes. I'll need to press this.
Yeah, or